Hi, welcome everyone to the last session of the day and the workshop. We're going to have a talk first and then a panel. So this talk, which is protecting high-value assets using robust MPC, will be given by Kelong Cong, who is a cryptographic engineer at Zama.
Right. Thank you for coming and thank you for staying till the last talk. I'm Kelong. I'll be talking about protecting high-value assets using robust MPC. This is a joint work with Daniel, Tor, Nigel, and Tituan. Although these are the names on the slide, but it involves many more people at Zama. So let me start with the motivation. On-chain finance is coming, whether you like it or not, and it's boosted by favorable regulatory conditions and technological adoption. There are many examples around the world, many banks, many brokers, and other financial institutions. They are tokenizing their assets, for example, the stocks, bonds, etc., to simplify trades and to reduce costs. But there's a very big problem with this approach, which is nobody wants to see their bank account, their portfolio, or their trades, transaction history. Nobody wants these to be seen by the public. For example, if I use my USDC or USDT to buy a coffee, the merchant can just look up my address and see the balance in my wallet. And this example extends to large institutions as well. And this is what Zama is trying to solve the confidential problem on blockchain. Now let me give you a small introduction of our MPC system that we use. But actually, before going into the MPC part, let me tell you a bit about what the overall Zama protocol does. So Zama is an FHE company, so we try to build confidentiality into smart contracts, and we do this by basically running FHE computation in the smart contracts, and because we want something called composability, where inputs from different users should be composable, meaning you can run computation on inputs from different users. That's why these inputs need to be encrypted by the same public key. If there's one public key, you also need one secret key. And of course, we don't want a central point of failure, so we distribute the secret key, and this is where the MPC part comes from. So yeah, so that wasn't what I just said. It's not, let's go into the picture. So here, if Alice wants to submit an input, she will encrypt it using the public key. That goes to a smart contract, and we have some off-chain components. One of them is called the coprocessor. This is the component that does the FHE computation, because to do FHE, it's actually really expensive if you just wanted to do purely on the smart contract. So it's done by an off-chain component. There's also a gateway component that's also kind of like an off-chain component that listens to events on the smart contracts, and it kind of submits requests to the MPC parties. And these requests will be like requests that only MPC can do. For example, distributed decryption and key generation. Now let's zoom into the MPC parties. So we have 13 partners running these parties. They've been running in production for, I don't know, like 4 months, and these are very well-known companies in the blockchain space. We have custodians, wallet providers, and other various service providers running these MPC parties, and of course running them fully independently of each other. And here's some details of our MPC protocol. Firstly, it's asynchronous because as you can see in the slide before, there are so many connections, and we cannot have any kind of assumption on the timing of message delivery because it's a very big network, and in reality, the network is not synchronous, so we have to make the asynchronous assumption. It's robust because we're handling requests that come from blockchain, and blockchain is it doesn't go down. There are always requests coming, and we need to handle them on time. So we cannot have things like failure with abort. We have to always handle every request, even if there's a party that's acting maliciously. Our MPC works with Galois rings over ZQ. This is simply due to property of TFHE, and that's the FHE scheme we're using. We focus on concrete security, which means we can have very good efficiency by using PISS in the offline phase, but as long as the number of parties is low. And we also support about like 1/3 corruption. And this is all the really technical things that I'm going to say. Really, you can look at Nigel's talk from RWMPC last year. I think you can find it pretty easily on the MPC Alliance website. And since last year, we've open sourced everything in this thing, samas-ai/KMS. It has been audited by 12bits, Zenith, and the Alexandria Institute. Okay, so I also have a slide on security in depth, which is pretty much the same as the slide from Blockdaemon. So we don't just want to have cryptographic guarantees, because things outside of cryptography can happen, like human errors or malicious insiders, for example. So we also employ security in depth, which means in our case we use the Nitro Enclave. So yeah, I'm not going to say this in too much detail because you already heard about it. But basically, the MPC parties, they run in a very secure environment, which has no networking, has CPU and memory isolation. The only way that the MPC party can communicate to the outside is through something called a VSOC, a virtual socket, and this allows us to be very, let's say, careful about what messages we can send out. And what I don't have on the slide is we also have remote attestation, which means other MPC parties can check that each other, they're running the same software, well, the correct software. Okay, so all that was, let's say, a bit of a long introduction. What I really wanted to talk about is the two very important events that happened since last year. The first is we did our distributed key generation for TFHE keys on Ethereum mainnet. So yeah, like I said, this happened on the mainnet. We generated these TFHE keys. If you are not familiar with these keys, there are many. It's about, I would say, 7-ish keys, bootstrapping keys, multiple bootstrapping keys, key switching keys, public keys, and of course there are secret shared private keys that are stored on the individual MPC parties. And with these keys, we officially start supporting running MPC computation on the mainnet. So this means users can encrypt their input. The coprocessors can compute on the user's input, and the MPC parties can do distributed decryption. And here are some numbers. It was a very long process. The offline phase took 54 hours. Online phase is much shorter. And we used a huge amount of bandwidth. per party, 10.5 terabytes, and also a lot of memory. The good thing is we don't need to do this all the time. So having it done once successfully is enough to bootstrap the mainnet. Now, why does it take so long? If you know about LWE ciphertext or bootstrapping keys, you know that they are basically, a bootstrapping key is basically a bunch of LWE ciphertexts. And in the ciphertext, we have this AS plus delta M plus E. A is public, S is secret, delta is some scaling factor, M is some message you want to encrypt, and E is some noise. In the MPC setting, S, M, and E, they become secret shared, and the important thing here is this E. It needs to come from something called a T-uniform distribution, and it's not super efficient to sample noise from a specific distribution in MPC. Well, I'm not going to tell you all about the protocol. Basically, we need to first have triples, which is easy, and then we need to turn these triples into bits. And what you see here, this chunk of code is how we generate bits, and each bit needs 2 rounds of communication. So there's a squaring. Don't know if you can see my pointer. There's squaring here and the opening here, so they need 2 rounds of communication. And for each element in the noise, you need b plus 1 bits, and b is a parameter from. It's a part of the FHE parameter, like 20-ish, 20, 30. So every noise will have like 40-ish rounds, and yeah, thousands and thousands of these noise elements that we need to generate. So that's one reason, and another reason is this is something also mentioned by the previous talk, is Nitro Enclaves introduces additional latency, because, let me quickly go back to the slides. So there's no, so the MPC node speaks TCP, but you need to always convert TCP using something called we use this socket process to do this conversion, and sends it over to the VSOC protocol. And on the other side, in the host instance, it needs to do the conversion back. So there's a conversion going out, there's also conversion going back, and all these conversion, translation adds additional latency. And these are some of the things we want to look into in the future to improve these translations that happens due to Nitro Enclave, and look into better ways to generate noise. Okay, now for the second important event, which is a sealed bit auction. And let me tell you about what this is. So the goal of this auction is to distribute SAMA tokens to the public, so anyone could participate in this auction. And these SAMA tokens are used to pay for using the SAMA protocol. Now, in a transparent auction where everyone sees what everyone else bids, you have a risk of bots that can front run your bids. That's why a sealed auction is better. And there's also another very important reason, which is it's the first big application that's using the SAMA protocol. So we built this auction completely on top of our SAMA protocol stack. Now let's go into a bit more detail on how it works. So when you submit a bid, you submit a table that looks like this. You have public price, like this is the price you want to pay per token. And then you have an encrypted amount. So in this case, this user mostly wants to bid, pay 0.1 USD for Sama tokens. And after the bidding phase closes, we basically put all these tables together and we sort them by the price from the highest to the lowest. And then we kind of check, we just add up the amount, and we add the amount up to a certain threshold that exceeds the supply. And of course, we do this all using MPC. And the threshold that exceeds the supply, the price right before it is the clearing price. And MPC is used in this process to, one is for doing public decryption, to decrypt, of course, the final clearing price. And also there's user decryption. So this means it's a decryption where only the user that submits the decryption request can see the results. And we use re-encryption for this. Yeah, so, and our distributed decryption protocol is much simpler than the key generation protocol. So given a ciphertext that looks like this, you have an A component and then you have the ciphertext. A is plus delta N plus E, same as before. You first run a local computation called switch and squash. So this is we call it a big bootstrapping phase. And then we do what's called a noise flooding phase, where we drown the noise, the original noise, using a much bigger noise. And then we open and reconstruct this delta M plus E part. And finally, we locally round to obtain M. So it's a very efficient protocol because you only need one round of communication. Now, let me give you some more numbers. So the supply is 880 million tokens, and at the end, the clearing price that the users decided was 0.05 USD. During this process, 121 million US dollars were shielded. Yeah, I didn't explain what shielding means. It's basically a process where you convert your stable coins, your ERC20 coins, into a confidential version of ERC20. And after you've done this conversion, you can participate in the blind auction. So this is the amount that was shielded. And there are many more numbers. There are like 24,000 bids. It was the -- 1 app on Ethereum for one day. So that was surprising. And during this process, we did 33,000 distributed decryptions. And the thing I think we're most proud of is we had 0 downtime during this process. So this is a really good example of showing that running robust MPC has its benefits. There's also a link below. This is a third-party link that has much more information about the auction and also the general status of the Sama protocol. Okay, yeah, so the main takeaway is our robust MPC system is effectively securing assets that are worth this much. And if you think about it, the MPC is protecting the private keys, and all the users are using the public keys to shield, to encrypt their tokens. And this is why it's protecting a lot of value in this way. All right. Thank you very much. That was the end of my talk.
Do you have any questions?
Hi, thanks for the nice talk. If you do a transfer from a shielded to a shielded account, how many transactions per second is the network currently able to do?
Very good question. So I think the current bottleneck is not the MPC part, but most likely the FHC computation. But this is mostly because we're still using CPU, but we'll have GPU ready soon, and then I think we should achieve much better throughput. But to answer your actual question, I don't have the latest number right now, but I would say 50 to 100 but it's 50 to 100 transactions per second, but it's enough. It's already enough, I think, to support all the transactions you can do on Ethereum. But if you want to add more chains, we need to do a bit more work.
Thanks.
We'll have time for questions in case there are more. Okay, if not, let's thank the speaker again for the talk, and we can move on.